Okay, so in this video we're going to talk about the ionization of water and how Ka and Kb are related to each other. So when you have water, sometimes what will happen is a water molecule will hit another water molecule and they will ionize, so they'll make hydronium and hydroxide. This only happens to a very small extent, but it does happen. So you can take the concentration of hydronium and the concentration of hydroxide and get an equilibrium constant. And that equilibrium constant is equal to 1.0 times 10 to the negative 14th at 298 Kelvin. So the concentration of hydronium and hydroxide are equal in water. And they'll be equal to 1.0 times 10 to the negative 7th. So as long as water is neutral, you will have an equal concentration of hydronium and hydroxide, and it'll be equal to this. Now, when you change the temperature, you may not have a pH of 7. Technically, it's still going to be neutral, though, because the concentrations will be equal. All right, so when you are looking at a base, sometimes the Kb will not be given. But we have pretty much all the Kas. So sometimes if you're given the Ka of an acid, you can figure out the Kb of its conjugate base. This only works if you have a conjugate pair. So ammonia, so if you're looking at ammonia, if you're given the Ka, or the Kb of this, you can figure out the Ka of its conjugate, which is ammonium. So it has to be a conjugate acid-base pair. So if you take the Ka and multiply it to the Kb, you'll get the equilibrium constant of water, 1.0 times 10 to the negative 14th. So if you're given a base, but you're only given Ka, you will need to figure out what Kb is, because you cannot use Ka with a base, and you cannot use Kb with an acid. Now, pKa and pKb are also related. They're related almost the same way that pH is related. So pH plus pOH is equal to 14. Well, so is the pKa and the pKb. So if you're given pKa, you can also figure out what pKb is by subtracting it from 14. So again, if you're given a base, you cannot use Ka. You will have to actually calculate for Kb. All right, so for hydrofluoric acid, the Ka is equal to this. You will have to give the conjugate base, write the equation for the conjugate base when dissolved in water, and find the pKa, pKb, and Kb. All right, so let's do part A first. Well, hydrofluoric acid, it's got that hydro prefix, so it's hydrogen and then some other element. So HF. So this is your acid. So if you want the conjugate, you're going to need to remove an H+. So if you remove an H, I get F. If I remove a positive 1 from this, I will get a negative. So that is my conjugate base. All right, so now it says write the equation when you dissolve the conjugate base into water. Well, okay, here's my conjugate base. Here's water. Since it's acting as a base here, it's going to remove a hydrogen, and I will be left with hydroxide. And then it's conjugate acid, which is just HF. All right, so now we're going to find the pKa, pKb, and Kb. Well, pKa, it was easy. I was given Ka, so I can just simply plug it in for that. So pKa is equal to the negative log of Ka, which is 6.8, times 10 to the negative 4, and that's 3.17. All right, so now I can find pKb, because I know that pKa and pKb, when you add them together, it equals 14. So 14 minus 3.17 will give me a pKb of 10.53. All right, so now let's look at, oh, and then also if you notice this, for pKa versus pKb, pKa is lower than the pKb of the conjugate. So that implies that hydrofluoric acid is a stronger acid versus fluorine as a base. All right, so the last step is to find Kb, which we can do because we've got pKb. All right, so pKb was equal to 10.53. All right, so now we just need to find Kb. We know that Kb, or pKb rather, is equal to the negative log of the Kb. So we just plug that number in. So 10.53 is equal to the negative log of this. All right, move the negative sign, so divide by -1 on both sides, and then do the opposite of a log, which is 10 to some power. All right, so when you solve for Kb here, you would get 1.47. Oh, wait, 1.47 times 10 to the -11th. Now, if you wanted to, you don't have to use this equation. You could say that the Ka times Kb is equal to 1.0 times 10 to the -14th. That is another way to solve for the Kb. It would give you the same answer though. All right, so the Ka value of ammonium is 5.8 times 10 to the -10th. What is the pH of a 0.10 molar solution of ammonia? What are the concentrations of each species? So this is an ice table problem. So if we look at this, we were given the Ka of ammonium. Ammonium is NH4 plus, so that's the acid. And we are looking at a solution of ammonia, which is NH3. All right, so this is my conjugate base, that's my conjugate acid. So I was given the Ka value of the conjugate acid, so I can find the Kb using what I know about Ka and Kb. All right, so let's go ahead and find the Kb because we cannot use the Ka for ammonia because ammonia is a base. So we're going to find Kb first. So Ka times Kb is equal to 1.0 times 10 to the -14th. Well, Ka is 5.8 times 10 to the -10th. All right, so now if I solve for Kb, divide out the 5.8 times 10 to the -10th. All right, so Kb is equal to 1.72 times 10 to the -5th. All right, so I have my Kb, so now I need to write out the equation. So ammonia is dissolved into water. Anytime that we're just talking about an acid or base, we need to be looking at what happens when it reacts to water. So ammonia is an H3. We're going to put it into some water. Well, ammonia is a base, so that means that the hydrogen is going to move over here and become its conjugate, which is NH4 plus, so we add an H plus, and hydroxide. So anytime we have a basic solution, we should have hydroxide on our product side. All right, so let's do an ice table. All right, initially, my ammonia's concentration will be 0.1. Water doesn't matter. 0 for both of my products. And change, well, minus x plus x for my products. So 0.1 minus x. All right, so we need to find the pH. So that means that I need the concentration of hydronium. Well, I'm going to get my concentration of hydroxide here because it's a basic solution. Once I get that, I can find my POH and get the pH. All right, so we're going to plug everything into the Ka expression or the Kb expression. So Kb is 1.72 times 10 to the negative fifth, and that's equal to the concentration of hydronium, which is, or not hydronium, ammonium, which is X, times the concentration of hydroxide, which is X, divided by 0.1 minus X, the concentration of ammonia. And so products divided by reactants. Well, we can approximate here because it's small. K is small, so let's get rid of that. So it's X squared divided by 0.1 is equal to this number. Well, let's get rid of the 0.1. And then once I do that, I'm going to go through and solve for X. And I should get, for X, 0.0013. So the concentration of ammonia is 0.0013, and it's the same for hydroxide. And then for ammonia, it's 0.1 minus 0.0013, or 0.0987. So now we have the concentration of each species, but I also need the pH. So I don't have hydronium here, which is what I need for a pH, but I do have hydroxide, so I can get POH first. So my concentration of hydroxide is equal to 0.0013. Let's solve for POH by taking the negative log of this number. All right, so POH will be equal to 2.886. So this isn't pH, so we need to subtract from 14. All right, so 14 minus this would give me my pH, which is going to be 11.11. All right, so anytime that you're given a base, remember you can't use Ka, you have to find Kb. And you can only do that if you are looking at a conjugate acid-base pair. So if they give you the Ka of the conjugate acid, that's fine. You can find the Kb from that and then use that number.